Hello everyone and welcome back to my lecture series on molecular docking. So in our previous few lectures, what we have done is that I have concluded my discussion with demonstrating you as to how do we generate this leak plot, which is basically a two-dimensional representation of your protein ligand complex. Okay, and using this leak plot, then you can kind of observe or identify that okay, these are the amino acid residues that forms hydrogen bond with my ligand through this particular atom, and these are the amino acid residues that might be in hydrophobic contact with my ligand. Okay, so such a type of analysis can be done when you have such a two-dimensional representation of your protein ligand system. Okay, however, in most popular journals, and you might have also observed in standard biochemistry books, that such a type of representation of protein ligand complexes or even protein complexes, they are shown in beautiful three-dimensional images. Right. So, in this lecture or in today's demonstration, I will show you as to how do you generate those three-dimensional images, those beautiful and graphic images that represent your protein ligand complex in 3D. Well, this is two-dimensional representation. Okay, so we would be using that Pymol software for generating these these three-dimensional publication quality images, right? In most of the research papers and biochemistry books, you would see the proteins are represented in ball and stick model, or in cartoon or ribbon representation, or even in surface representation, and that makes your manuscript look visually stunning. And using such images, that will be a kind of visual treat for the reader, that would attract his attention, and that would you to enable you to express these molecular interaction in more vivid way, right? So it is also necessary that you learn how do you generate those three-dimensional images, right? And that is what we are going to do in our today's session, right? So let us begin. So we would be using this same protein ligand complex, 4-methoxyflavone in complex with our cyclooxygenase 2 in 2 protein molecule, right? We would be using same leak plot. We would be referring to this leak plot. Okay, and let us see, by the end of this particular session, you would learn a lot of new things. You would learn how do we work with Pymol, what are the different commands that can be used, or one after another, or that they can be even mixed and match to generate beautiful three-dimensional images of your protein ligand complex, or to render your protein ligand complexes effectively. That is what our today's discussion is all about. Okay, so let me minimize this. We are going to come to this slide, this particular picture very frequently. Okay, so now for generating those three-dimensional images that are of publication quality, well, let us begin. We would require our protein ligand complex, right? So this is COX-2 4 prime methoxyflavone complex that we have generated in our previous step. Well, now let us begin with this complex and generate, you know, a very good and vividly looking uh, illustration for your, maybe you can use those illustration in your project report or in your research paper or even in your PhD thesis. Okay, so let us begin with this. Okay, so this is the first time I am using or demonstrating you how do we use this Pymol. So let me first tell you about this software. This software is developed by Delano Scientific, and this is also one of the open source software. You can get some version of this software free. Okay, all you have to do is to search on internet, on Google, Pymol download, using these two terms. You would end up with a link. Follow that link and download the binaries or MSI file. Install it, and after installation, you would be ready to go. So when you open any of the PDB file in Pymol, it might look something like this. So by default on my PC, PDB files are PDB files are set to be default open by your Pymol. Therefore, if I double click it, it directly opened it. Okay, so if Pymol is not your default software, then after opening this Pymol, you can go to this file and use this open menu, and then browse to the location where your PDB file is located, and you can open it then. Well, this is another method, right? So this is how you open it. Okay, and when you open any molecule, two windows are usually uh, opened, right? So this is the, you can call it as main window, and this is the molecular visualizer, where you can rotate and see what changes are happening in your molecule as we proceed. Okay, and over here there are some shortcut that I will demonstrate you how do we use them. Okay, so these things become handy. All these menus are also available in your main toolbar. Okay, so it becomes handy when they are present nearby, right? So these are the two main windows that this Pymol opens with. Okay, so now as usual, when you open any file in your Pymol, by default it is opened in this CPK representation, in which all carbon atoms are colored in green, nitrogens are colored in blue, while oxygens are colored in red. If there are sulfurs, they would be colored in yellow. I don't see it around, right? So yes, here you have got this yellow colored disulfide bond. So these might be cysteine residues, right? So by default, what you see now is CPK representation, or what we call it as a line representation. Okay, so now what our ultimate objective is that we want to create a three-dimensional image that would focus on this interaction. We want to show that our ligand is hydrogen bonded with serine 530. The same ligand, the ligand is hydrogen bonded to serine 530 through the oxo group of our flavonoid molecule, while the side chain of tyrosine and side chain of this arginine 120 is hydrogen bonded with the methoxy oxygen of our ligand 4' methoxyflavone. And we have to also figure out some way to show that all these residues are in hydrophobic or van der Waal contact with our ligand. That is what our objective of creating the image is. Okay, so you should always remember that whenever you create an image, you know uh, each and every image should tell some story, and the story should be clear in your mind before you start, right? So it should be very clear in your mind as to what exactly do you want to focus in that image, and appropriately then you can start out using these software to generate those beautiful three-dimensional images. So for time being, I have just explained you as to what do we expect in our image. We expect that there should be this ligand molecule, flavonoid 4' methoxyflavone, that is hydrogen bonded with these three residues, and we want to show that there are these residues that are in van der Waals contact. So this is an overall idea of the image that we want to show. So, and this idea should be quite very clear in your mind before you start out generating these three-dimensional images using these softwares. Okay, so to begin with, so in order to do this task, we would need all of these amino acid residues that are hydrogen bonded, your ligand. They should be represented in proper way, right? So that you can focus on, or you can attract the attention of the viewer easily using some representation, right? So I would also guide you as to what kind of representation would you like to use when you kind of create such images. Okay, so by default, the protein molecule that you load, it seems to be quite chaotic. Nothing is quite very clear in it, right? So we want to create first this scene first on our Pymol, and then we would see how can we beautify it. Okay, how can we add some cosmetic touch to make it look more beautiful, right? So first let us make our view clear so that we can clearly visualize all the corresponding molecules that we want to focus in our picture, right? So let us start out working with this Pymol. Okay, so what is that we want? We want to focus on our ligand, because when you work in medicinal chemistry or in any molecular modeling stuff, your major focus would always be, say, some chemical molecule that you might have synthesized in your laboratory, or you might have performed activity of those molecules, right? So there would be some molecules that would usually be the main focus of interest, right? So let us then make sure that these molecules remain the focus of interest in our view as well, right? Just a minute. Okay, there was some problem with my monitor. Okay, well, let us see how we can focus on our molecule and the interaction, right? Okay, so our main focus of the story is the ligand molecule, right? And how do we locate in this mess as to where the ligand is? Okay, it is quite easy. Do you see the sequence over here S? That if you click over here, it will show you the sequence of your protein molecule that has been loaded over here. So all you have to do is to use this scrolling bar, go to the very end of your sequence, and you can see that you have got ligand over here. So when you click on this ligand, it would be selected, as you can see over here. It will get selected, and this whatever is selected would be turned in green. And over here you can see one more selection menu has appeared, right? So this indicate that whatever you have selected is your ligand molecule. Okay, and using Pymol, Pymol usually work by creating object. If there is provision of creating objects in Pymol, and that is how usually people work. So whatever you want to focus on, you would create an object out of those amino acid residues or those ligand molecule. Okay, so over here our objective was to focus on this ligand and these three amino acid residue. So we would work by creating a separate object for serine 530, tyrosine 355 and arginine 120 along with your ligand 4' methoxyflavone. Okay, so that we can focus on each and every object then separately. Okay, so for creating object you need to first select your amino acid residue or whatever residue you are interested in. In our case we are interested in ligand, and we have selected this ligand, right? A selection menu appears over here. So this is not an object. We need to create an object out of this selection. Okay, and for creating object you have to use this action button. This is called as action button, the A written over here. So if you click on this action button, there is an option called as create object. So whatever you have selected, we will create an object of that selection, and for time being we have selected ligand. That means by doing this thing you are creating an object of your ligand. That is what we will do, right? We have create an object. It will clearly mention over here, okay, the object one has been created. So now we no longer need this selection since we have created a separate object out of it. So what you can do is that you can simply delete this selection. Okay, so there would be a lot of objects that we are going to create, and later on after 2 or 3 months you would completely lose track as to what was object 1 and what was object 2. So it is better that once you create this object you rename those object properly, so that next time you open your Pymol it would be quite clear for you as to what this object is all about, right? So for that what we can do, we can again go to action, and you can rename the object. Okay, and we would rename this object as our ligand or 4' methoxyflavone, right? 4 underscore mf, that would correspond to your 4' methoxyflavone, right? And when you hit enter, your object has been now renamed. So every time you open now, it would be clear for you that this object belong to your ligand, right? Okay, so similarly this is one of the way of creating the object. Now there is another way of creating the same object. You can use your commands for creating object. Okay, now in your main window there is this particular area wherein you can type a lot of commands, and I will show you as to how, what command that you need to learn in order to create object. Okay, so that command is called as create object. So we'll say for example now we want to create the object for this residue serine 530, right? So let me show you how do we create the object for residue serine 530. So if you want to create an object using this command, you would have to give keyword called as create. Create is a keyword that would be interpreted by this software, that whatever you write after create, that would be intended for creating some object, right? So we would use this create command. Then the syntax is that when you use this create command you have to give the name of that object. In our case, well, let us keep it simple. Well, let us name our object as serine 530. So so far so good. This object, this particular command will create an object called as serine 530, and as per the syntax you are supposed to give a comma, and then you would have to tell your software as to what residues are supposed to be included in this object. Okay, so for that you would have to give this keyword res id, that is residue id. So we are going to create an object for an object called as serine 530, and this residue is located at position 530. This is what this command means. Okay, so I will repeat it once more. Create serine 530 means that you are supposed to create an object whose name is serine 530, and this object is supposed to be created by the residue which is located at number 530 in your sequence. Okay, res id means what is the identifier of that residue. So since our serine is located at 530th position, the residue id would be 530. Okay, and once you write this command, and you are supposed to hit enter, right? And now it says that object has been created, right? And there are 6 atoms found in this object. In this way you will create the object for remaining 2 residues as well, tyrosine 355 and arginine 120. Well, let us create these residues now, these objects now. Well, now there is a shortcut. What you can do is that when you give a command, your Pymol remains, your Pymol remembers as to what command have you given in the previous while, before you since you have started this instance, right? So and in order to see what command you have given, you can use the upper arrow on your keyboard. So if you hit upper arrow, it will tell you as to what command you have given. So I have just hit the upper arrow, right? And now it shows me over here as to this is the last command that you have given. Okay, so all I have to change is the syntax. We can use the same command. All we have to do is to change the numbering of amino acid residues. So now we want to create an object named tyrosine 355. So we would write over here the name of the object as tyrosine 355, and what would be the residue id? The residue id would be 355. Why? Because tyrosine is located at number 355 in your sequence, therefore residue id is 355. Again, then hit enter. Now you can see this object is also being created, and the final object that we want to create is for Rg9 120. You would create an object for Rg9 120 as well. So if I again hit on that upper arrow on my keyboard, you will get something like this. So last command that we have given was creating an object 355. If I again hit the same upper arrow, it will show me what was the command that I gave before that tyrosine 355 object creation, that was serine 530. Okay, so in this way you can toggle between all the command that we have given so far, right? So now our objective is to create an object for Rg9 120. So what is the name of our object? The name of our object is Rg9 120, and this object is supposed to be created by residue at position 120. That is what it means, right? So we would then hit an enter. As you can see that the objects are now being created, and the same objects are also shown over here, right? Okay, so this is what our main focus of the figure would be: the ligand and the three amino acid residues that are in polar contact with the different atoms in our ligand. Moreover, we would also want to show that these are the few amino acid residues that are in hydrophobic contact with our ligand. Well, we would also create an object for these ligand or object for these amino acid residues as well. Okay, so let us create an object, but instead of creating instead of creating an object separately for each and every amino acid, since all of these amino acid residues are in hydrophobic contact, we would create a single object in which we would club all of these amino acid residues. Okay, and how do we do that? I will just demonstrate you. Okay, so this is what we have done. We would create an object, and let us say that since these residue correspond to hydrophobic contact, we would name this object as hydrophobic, HYD. Okay, and we would give residue number one after another. Okay, so I have already figured out, or I have already copied these names of this residue in a separate file, and I have written them in residues in non-polar contact. I have already done it. So what I will do is that I will copy this thing. These are all the amino acid residues that are listed over here in hydrophobic contact, right? So make sure that you do it beforehand, right? Copy all of these amino acid residues and place them serially one after another. And by that I mean serially means what? Amino acid at amino acid number 116 should come first, while the last amino acid residue is 527. Okay, so you have to make sure that they are present in serial order when you when you write them in this list. Okay, you have to do that as your homework, right? So I would copy this, and I would paste it, right? In our Pymol syntax, we do not need the name of the amino acid residue, but we would require the number of the amino acid residue. So instead of giving like residue ID valine 116, it would be enough if you give the number of valine, that is 116. So your Pymol would identify that whatever residue is present at position 116 is to be included in this object called as hydrophobic or HYD, right? So in this way we no longer need the name of this amino acid residue, therefore we would delete it. Okay, let me delete these amino acid residues. It won't take much time, right? So this is what this command will mean. We are creating an object called as hydrophobic or HYD, which will be comprised of the residue with identifier 116, 349, 384, 385, 387, 522, okay, so on and so forth. Okay, so always make sure that these residues are arranged in ascending order. That is, the residue ID, the lowest residue ID is written first, and the highest residue ID is written last in your command. Otherwise, this command will not work. Okay, and then just hit enter. Now it said that it has created hide object, and there are only 7 atoms, which is not what we intend, because there is a gap over here. So in this hide object there are currently only 7 atoms, and 7 atoms are for this residue number 116. It says how many atoms are there in your object. So if this much number of amino acid residues are present in your object, then of course logically the number of atoms that would be involved in this object would be very high, and we have got only 7 objects over here. Therefore that means something has gone wrong. So it would be better that you can also delete the object this way. I have deleted this object, and maybe there is a syntax error that I have placed a gap over here. Do you see? There is a gap. So I need to remove this gap so that now all of these amino acid residues would be incorporated in this object called as HYD or hydrophobic. And I will again hit enter. Yes, now the number of atom has increased from 7 to 72, and we are on the right track now. Right, we have got this hydrophobic object, right? Okay, so we no longer need to see this sequence, so you can make it go away by clicking on this S. The thing is that we have only created those objects. Now let us focus on these objects now, right? For doing this, we would well, one more thing we can do, right, is that let us show our protein molecule in cartoon representation, right? And for that, showing it in cartoon, let us use all of the amino acid residue in our protein sequence as a separate object. Okay, so in order to select entire protein into an object, you need to select on first amino acid residue. It has become green, that means it is been selected. Then click on your shift button on your keyboard, scroll your bar to the end of the sequence and select the last amino acid residue. By doing this, you can see that everything in your protein molecule is being selected now. Do you see? It has become pink. That means each and every atom has been selected. Okay, and we would create an object out of it. Action. We would create an object. We no longer need this selection. Therefore, we can delete this selection and let us rename this object now. Rename this object as cartoon representation, because that is what we are going to use it for. We are going to create a cartoon of this particular sequence, right? So everything is in place now, and let me hide the sequences. Okay, so let us try to build up our refine image now, right? So this is what we have loaded. Using this hide, you can hide whatever you wish. In our case, now I will hide everything. Okay, in all I will hide everything, and one by one I will show you as to what we need to show, right? So let us say that if let us show our ligand as in sticks representation. So this is the stick representation. Okay, you can right click on your mouse and drag down so that you can focus or you can bring it into focus, right? You can also translate your molecule by clicking on your rolling button on your mouse. Click that rolling button and then you can drag it left or right, up or down, in order to place it wherever you like. The scrolling button, or you can say the scrolling roll that is present in your mouse, you can click on it and then translate it wherever you wish. This thing can also be done. Or alternatively, if you want to focus on your ligand molecule, you can go to action and zoom. It will focus on whatever molecule you have selected, right? Now similarly, we would show our serine 530 also in sticks representation, right? It has been shown over here. If you right click and drag up, you can kind of visualize as to this serine is also visible now. Similarly, we would also show our tyrosine 355 in sticks representation. Here it is. Similarly, we have got hydrogen sorry, your Rg920, we will also show it as sticks representation. Here we go, we have got our hydrogen. Okay, now you can rotate your scroll to have a better representation, right? So what is the level of slabbing you want, you can focus it by using your scrolling button. Okay, don't click on it, just roll it up and down. Okay, so in this way you can decide what would be the depth of the slab that you wish to focus on. So these are the three residues that we would be interested in, that we would be focusing on, right? So you can say now that these three amino acid residues are in sticks representation, right? And to differentiate our ligand, well, let us show our ligand in ball and stick representation, and let us keep our interacting amino acid residue in sticks representation, right? So now as you can see, in your show command there is nothing like ball and stick. You can show it as lines, you can show it as sticks, you can show it as ribbon or cartoon. So there is no option, or there is no way currently the software that I am using, there is no way that you can create a ball and stick representation. And well, since we want to show our ligand into ball and stick representation, there is some other way around that I am going to teach you as to how you can create a ball and stick representation in your Pymol, right? So for doing that, we would use this show command. Okay, so what you are supposed to do is that we would use this show command, and show command requires as to what do you need to show. We want to show one of the object in spheres, right? Show sphere, SPHERE. But what is the name of that object? We want to show sphere 4 underscore MF. That is, this is the name of the object of our ligand, right? And this is what it means, show sphere for our ligand. Okay, now if I hit enter, the ligand is no longer being shown in sticks, but it is shown in spheres now, right? So now what we will do is that we would reduce uh, the radius of the sphere, right? And in order to reduce the sphere, you would use another command called as alter command. If you want to use this alter command, the syntax is that you would have to write alter, and then you would have to tell what is the object whose structure is needed to be altered. And the name of our object is what? 4 underscore MF, right? And then how is that you want to alter? You want to reduce the van der Waal radius of that particular sphere, right? So for that you need to tell that you need to change the van der Waal radius, and that van der Waal radius should be initiated with the value of 0.4. By default it is initiated with the value of 1. Okay, so if I decrease the value of van der Waal radius, eventually the sphere's radius would decrease. Okay, so this is what it means. Alter the object name 4' methoxyflavone by decreasing the van der Waal radius to 0.4. This is what this command means, right? And then you are supposed to hit enter. Okay, it appears that nothing has happened because we have to use another command called as rebuild. Rebuild command would again rebuild this the view that you are seeing. Okay, after use rebuild command, now you can see that the the size of sphere has been decreased to 0.4. Initially it was 1, right? So now you can see the ligand is in ball and stick representation. All the atoms are represented by ball and all the bonds are represented by sticks. So such a type of representation is called as ball and stick representation. Okay, while the amino acid residues that are interacting with your ligand, they are still in sticks representation. Well, this would be a good contrast so that you can later on identify that our ligand is in ball and stick representation, while our amino acid residue that we want to focus are in simple sticks representation. Okay, well, now let us again do something by which you can visually distinguish your ligand. Well, let us change the coloring scheme of our ligand, right? So you can change the coloring scheme using this coloring option, right? Click over here, color by element, and will let us color all the carbon atoms in your ligand by yellow. So if you select this, now you can see the carbon atoms in your ligand are now being colored by yellow, while the oxygen are still colored in red. Over here, the carbon atoms are colored in green, while the oxygen and nitrogen are colored in red and blue respectively. Okay, so in this way, now visually itself you can say, okay, this is my ligand, and whatever it is present in green carbon, those are my interacting amino acid residue. Good. So this is how we have done, right? We have made sure that our view now only contains ligand, three of our amino acid residue. Well, now let us focus on how do we show these hydrogen bonds, right? I will tell you now as to how do we show our hydrogen bonds. So there is no direct way in which you can show hydrogen bonds in Pymol. For that, what people usually do is that they use this measurement wizard, right? So there is measurement option in wizard. You are supposed to use this wizard menu, and in this wizard menu there is a sub menu for measurement. Okay, and when this menu is activated, you know uh, measurement measurement stuff, or you can say measurement commands are seen over here. Okay, now let us first distinguish where is that hydrogen bond, right? So the first hydrogen bond is between the side chain oxygen atom of our serine 530 and the carbonyl oxygen which is present on our flavonoid ring. This one. Well, let us focus on this hydrogen bond first. Okay, so here is our carbonyl oxygen. Okay, and it is in hydrogen bond with this serine side chain oxygen, right? So since this is again active, it is kind of telling you, or it is kind of requesting you that pick the first atom that is involved in your measurement. So we want to measure what is the distance between this oxygen from our ligand and this oxygen from our protein molecule. Okay, so once you are done, you can click on done. So this is basically your hydrogen bond, which is 2.80 Armstrong in length. You can see we are talking about the same hydrogen bond, right? So similarly, we want to also show the hydrogen bond between the tyrosine 355 side chain hydroxyl group. Okay, and we also have this hydrogen bond between the guanidino group of Rg9 120 and the oxygen from our methoxy group from our flavonoid, right? So in the similar way, we would kind of create hydrogen bond as we have created in case of serine 530. Okay, so in order to identify which amino acid residue is you are dealing with, you can also label them, right? We can label serine 530, we can label residue so that the label appears over here. You can also label the residue tyrosine 355, and you can also label the residue RG9 120. It is a handy way for you to keep track of what is the measurement that you are doing, and which is the amino acid residue that you are dealing with. Okay, so for time being we are only having three amino acid residue over here, but it might be possible that you might end up having say some 12 hydrogen bond that involves in say some 8 amino acid residue. In such case it would be very difficult if you don't know what is the amino acid residue number that you are dealing with. Okay, so now we know that we need to create hydrogen bond between this atom and this atom, and the methoxy oxygen and the nitrogen from your guanidino group, this atom. So for that we would use this wizard tab and use this measurement option. Click on the first residue, click on the corresponding second residue. This particular hydrogen bond is 2.74. Just make sure that 2.74 is the length of hydrogen bond that you have detected in your lick plot. Yes, we are going in the right way. And similarly we need to show the hydrogen bond between this guanidino nitrogen and methoxy oxygen. This hydrogen bond is with length 3.18. Let us confirm it. 3.18. Yes. So these are the hydrogen bonds we need to show in our figure. Now since we are done, let us click this done. Okay. And I usually don't prefer to show the bond length over here. Therefore you can also hide the label, hide the label. Okay, you can also hide the label of all the measurement that you have made. So these measure 1, measure 2, measure 3, these objects now correspond to the hydrogen bond. Well, let us deal with the coloring of this hydrogen bond later on, because things are going to change as I have planned. Okay, so one more thing that I now wish to tell you is that you should always save whatever work you have done, right? So let us first save it as a save session. Okay, and let us call it as test. Okay, and it would be saved as Pymol session file, and it will have extension PSE. Okay, and let us save it. Okay, now you can see that test.pse file has appeared over here. Well, now the thing is that once you have saved, and unfortunately if the computer shuts down or if the program crashes, you can again open this Pymol session test.pse file, and you can begin with the place that you have saved last time. So always keep this good habit of saving your work in intermediate stages, so that you don't have to do things right from the beginning, right? So this is how you save your representation in a Pymol session file or PSE file. Okay, well, now this is the basic thing that you need to focus, right? So what we will do is that we would now show our protein molecule in cartoon representation. One more thing, we have dealt with hydrogen bonding and amino acid residues that are involved in that hydrogen bonding, but still we have not shown these amino acid residues that are present in in and around the vicinity of your ligand, and they contribute in a non-polar fashion, or they have non-polar contact in form of hydrophobic contacts. Okay, well now my plan is to show them into surface. Okay, so that you can identify that whatever surface is shown, that surface is of the hydrophobic amino acid residue. Okay, so what we will do is that we now know that we have created a separate object for these hydrophobic amino acid residue, and now let us show that object as a surface. Okay, all you need to do is to go to hydrophobic or HYD object, and then go to this show command and then select surface. Now you see that whatever residues that are in hydrophobic contact with our ligand, they are shown in surface representation, right? But this surface representation is, it do not appear to be quite well resolved. Okay, well, let us deal with its resolution first, and let us color it properly so that our representation might look beautiful, or you can say it might look attractive, right? So for doing this, well, I think let us first change the color of this surface, right? So let us color our surface in a shade of maybe cyan, and we can use green cyan. Okay, it will or maybe we can use some other color cyan. We can use this pale cyan. Okay, and coloring is not really my very good this appears to be good. Okay, okay, what we have used for coloring, we have used this aquamarine or green cyan, I suppose. Green cyan, I suppose it was green cyan, right? Okay, so final. Okay, now let us see what we can do about the resolution of this surface, right? So it looks quite coarse. Well, now let us make it more refined. Okay, and to increase the refinement, what we can do is that we can adjust the solvent radius that we have used for creating this surface. Okay, and to adjust the solvent radius, you can use this set command. So we need to set the solvent radius. Okay, we need to set the solvent radius to the value of 1.0, right? When I hit enter, solvent radius has changed to 1.0. Okay, and we can again refine the quality of the surface by using this again set command. Okay, and we would be setting our surface quality with a value of 2. It will take some time. Okay, now you see that these surface now looks quite more well defined as compared to what we have generated by default. It looks quite nicer now. Okay, so we are good, right? Okay, now let us think of adding some more cosmetic stuff to make it look more attractive, right? Well, let us show the cartoon representation now. Okay, we have already created an object for this cartoon representation. Now we would show it as cartoon. Okay, but when we show it as cartoon, you know, things have become complicated, and it appears that we lose our focus from our interaction, that is the main objective of our representation. And in such case, what we will do is that we would show them, we would show these cartoon representation, but at the same time we will have to make sure that the focus of the viewer is not is not uh, deliberately taken away from this interaction. Okay, now there is a way. What we can do is that we can color it in say white color in a, okay, and next thing that we will do is that we will make it transparent so that the focus will always remain on our ligand and amino acid residue, right? So if you want to change the, if you want to make it transparent, you would have to go to this setting command, setting menu, transparency, and we want to change the transparency of our cartoon, and we want to make it 40% transparent, so we would use 40%. So now you can see that the cartoon are, we have maintained the transparency of cartoon at 40%. Moreover, we can also change the edges of this cartoon to look more fancy, right? So for doing this, again we have to go to setting, then select this cartoon and show this cartoon helices or alpha helices in your cartoon representation in fancy helices. When you see these fancy helices, when you select this fancy helices, you know, the shape and orientation, or you can say the shape and texture of your helices would change and it would look more fancy. Okay, well, now let us again focus on our ligand, because that is what the major topic of interest is. Okay, so let us zoom on our ligand. Okay, we have zoomed on our ligand. Okay, I will scroll out so that, so as to we adjust our slabbing, right? I will right click and again come out of the view, right? What I am trying to do now is that I am trying to focus my view in such a way that I can clearly see the ligand and the interacting amino acid residue. Yes, this might seem well. Okay, yes, this appears to be good. Why? Because we can clearly see serine, we can clearly see arginine, we can clearly see tyrosine 355, and we can see this ligand as well, right? But some portion of our ligand is being hidden behind this surface. So what we can do is that we can also change the transparency of surface by setting transparency. Over here we would select surface and make it 40% as well. So now you can see that this carbon that was previously hidden in behind this surface representation, now you can clearly see it. Okay, maybe I will bring it in center, right? So let me save it first. File, save session, so that by mistake if something unfortunate happens, we don't have to begin it right from the beginning. All right, we are good. So what we can do is that we can also display the background in white. To do that, you have to go to this display and change the background color to white. Okay, now things appear to be quite very good, right? But when I change the color to white, the hydrogen bonds now are not quite vividly visible. So I think we need to change the color of our hydrogen bond, right? So let us use some contrasting color. We can use some shade of magenta, like hot pink. Now you see that the color of the hydrogen bond has changed from yellow to hot pink. We would do the same thing with other remaining hydrogen bonds. Would change the color to hot pink. Now it appears in hot pink. This is what we want. Okay, well, now let us worry about some more things. Okay, uh, well, now either you can keep these hydrogen bonds in a dashed way as they appear over here, right? Or you can also make it look like a continuous hydrogen bond. For that, what you would have to do is to change the distance between these dots. Okay, so you have to change the distance between the dots in this dash, right? So for that there is a command called as dash gap, and you can use this set command to set the gap dash, or you can say dash gap. What we are supposed to do, we are supposed to set the dash gap to the value of 0.01, so that the ultimate objective is to create or to set the dash these dots in this dashed line so very close that it would appear that it is a continuous line. That is what we have done in this command, set dash gap to the value of 0.01. Okay, and if I hit enter, now you can see that the hydrogen bond appears to be continuous now, and it looks good. Okay, one more thing that we can do is that now let us focus on these labels. The labels are not very clear, they are in green, right? So moreover, most of the hydrogen bonds are originating from side chain, and there is no point of keeping the atoms from main chain from our interacting amino acid residue. So what we will do, we would hide the atoms from main chain. Okay, what you are supposed to do is to go to this amino acid residue, use this hide command, and select this main chain. Now you can see the atoms of main chain has been, or you can say backbone, are now hidden, and only the atoms from the side chains are shown. You do the same with tyrosine 355. Now after doing this, you can see that only the side chain atoms would be shown in stick, while the main chain atoms we can hide them, right? Use this hide command and hide the main chain, right? And same we would do with Rg9. We would hide the main chain like this. Okay, after doing this, we can also change the color to we can change it to white, right? It would look good. You can also change the color to white, right? So change the color to white. It is all up to you. I like the typical ball and stick CPK representation. That is why I am doing this, right? So when we change the color to white, somehow the color of the color of label has also changed. Well, now there is an option to change the color of label, right? So what you can do is that we need to change the font of our labels now, and to change the font, we would be changing the font ID first. Okay, you can do this by using this set command. What do we need to set? We need to set the label of font, and we are supposed to use some another identifier, and the name of the identifier is 7. So this is what it means. We are going to change the label font with an ID 7. Okay, now things have changed. Well, now let us change the color of our label. We are going to use same set command, but we are going to set the label color, and we are going to set the label color to black. And when I hit enter, now you can see the label has changed the color to black. So you can also increase the font size. Okay, so what you can do is that you can increase the size of your label by using this again set command. Set label size to have the font of 20. Now you can see when I hit enter, the size of the font would increase. Now it would be clearly visible, right? Okay, things are good now. Okay, so again I will save the session, right? And there is one more thing now. This Pymol offers a very good feature, and we call it as ray tracing. So when we use this ray tracing function, it will give an effect of lighting, and there would be shading, and there would be fog effect clearly and quickly visible, right? So if I use this ray tracing function, you can activate this tracing function by using this ray command, right? And hit enter. It might take some time for this ray tracing, so just be patient. Okay, now you can see that things have changed a little bit, right? So you can see that there are shades over here. Some of the helices, its shade is shown on the surface, right? Here is the shadow of your ligand shown on this surface. So it looks really very beautiful, right? So this is now, this image looks quite visually stunning, and you can then use this file and save image option, and you can save it as test.png and save it. Okay, let us see how your test.png image looks like. You can right click it, preview it, right? And you can see that this is how you have created a beautiful image of your protein ligand complex, right? But there is still some problem, there is still some issue, right? And issue being that this is still a low resolution image. Okay, by default, when you use this plotting image function, uh, it creates an image with low resolution, right? So what exactly I mean is that if you try to zoom this image, you can already see that this picture start to pixelate like this, right? At this particular resolution, right? And this is usually not a very good feature when you publish a kind of research paper or when you publish it in a book, your publisher would ask you to give the images in very high resolution. Okay, so how do we manage this resolution now? I will just let you know how do we do that, right? So these things can also be done in Pymol. Okay, I will just show you. Now, if we want to have an 8 by 6 inch image with 600 dots per inches, then there is a command called as ray command. Okay, so you can use a variant of this ray command in which you would say that I want to ray trace my image with the number of pixel on x-axis as 2400. That would mean there would be 2400 pixel on my x-axis and 1800 pixels on my y-axis. Okay, that is what I want to ray trace it. Okay, and then you can hit an enter. So now your Pymol is creating an image which is 2400 pixel in width and 1800 pixel in length. So that would be eventually 8 by 6 image. Okay, you might want to need to be patient when these things happen. It might take some time, or even sometime uh, this software crashes also. Well, let us keep our finger crossed and hope that this software will not crash and it would retrace the image in the dimension that we need. You just need to be patient. Half of the things are already done, and when it say it is not responding, just make sure that you don't click somewhere inside, otherwise the program will crash. Let it do its work uh, with its own way, so don't disturb it. It's already done, most of it is done. Yes, now it says that the image size has been set to 2400 pixel on x-axis and 1800 pixels on y-axis. Okay, and now to render it in an image, we can use another function called as png. So png function is to export the image in png format. We are going to use this pinch and write the name of our image. I will rename it as test uh, 8 by 6, right? This would be the name of image. I will give it a name png extension. This would be the name of the file that would be created. Okay, and we can set the resolution with 600 dpi. Dpi is equal to 600 dot per inches. Okay, so when I hit enter, it wrote a kind of image file named as test 8 by 6.png, and it is having the resolution of 2400 by 1800 and with the resolution of 600 dots per inches. Okay, now 600 dpi is standard image resolution that is required by most of the publishers like Elsewhere or Springer or even Nature or PLOS ONE. They would need those images in 600 dots per inches. Okay, if you read their author to instruction in more details, over there they expect the image to be of quite high resolution. Okay, so now let us check if the resolution of this new image, that is 8 by 6 inches with 600 dpi, is better than what we have done in the previous task. Okay, so now this test image that we have created, if we preview and if we try to zoom in, it start to pixelate, right at this level. Okay, well now let us see the next image and try to zoom in. Now you can see, even if you go into this much details, it still don't pixelate. Well, that means this is a high resolution image, and this, my friends, is a low resolution image because it start to pixelate. Okay, so keeping an high resolution image, there is a drawback that the size of the image would also increase. So the low resolution image is only 238 kb, while the high resolution image is 1.51 MB. It is the same image as it might appear, right? So it might be the same image. The size has somehow increased, and the resolution has also increased. So in this way, my friends, you can create high resolution publication quality images using Pymol. So that is all, folks, I have for you today. See you guys in our next molecular docking session. Okay, so goodbye for time being.